So currently I do lots of work around water. I was trained as a water chemist. I have done research on water. My love right now is water policy, both for the state and nationally. And a lot of people say, well, how did you get to be a water person, especially as a chemist? And it really starts back to when I was a kid. My parents and grandparents and aunt, we had a family place up in eastern Ontario, in the Lake District in eastern Ontario. You could only get to our cabin, and it was a cabin, not a cottage. And you had to get there by boat. It was very remote, and it was on a beautiful lake, 300-foot deep lake, 9-mile long, lots of islands. It was an incredible place to spend my childhoods, and I spent every single childhood until I started working at 17, up in that lake, in that cabin, living a dream, I'm sure, that most kids only get for a week at camp, and I got to live it for 6 to 8 weeks every summer. And I fell in love with water. I fished with my dad, I went swimming every day. My mom had been a swim instructor, so we learned to swim probably before we could walk, I'm guessing. And it was just a wonderful place to learn to love nature and learn to be so comfortable in it, because we literally were 50 foot from the water, and we just treated the lake and the land and the animals there all just as if it was part of our world. It was all one thing. When I then went to college, I was a chemistry major, and I loved chemistry, but I have to say and I'd say my career, my life, it's really a life, has really just done a lot of zigzags, which is great. Little things just, one little puff of the butterfly wing, and things just, changed course. And in college, I had a professor who, I went to Grinnell College, and Grinnell had a requirement that all freshmen take a writing class. And it had to be in chemistry, but the professor got to choose a topic, and then we wrote papers throughout the semester. And he didn't just grade them and give them back. He graded them, gave them back, and required us to keep rewriting them until we got an A. Very different experience. So, an aside, I also learned how to write at that time. And I took a class in water, and he had us read 3 books on water and write essays around those books. And that's when I realized you could actually do chemistry and water in the same breath. So when I left college, I wanted to go do environmental chemistry, water chemistry, study lakes and rivers. And the faculty at Grinnell they were very encouraging. They said I could easily get into graduate school and do very, very well. But they didn't know anything about environmental chemistry. This is the 1970s, and it was more of a fad than an arena that was taken very, very critically as an academic career. And so I waited a couple of years, and I worked for a while, and then I went back and looked at graduate school, and sure enough, I got into a program at the University of Wisconsin-Madison. And again, I had applied to one program, but the person who wrote me the acceptance letter for grad school was in a different department. And he said, these guys got your letter of inquiry, and I think you would do better with us. And so I went to that program, which was water chemistry, and I had a fabulous experience there. I got a master's in water chemistry and then a PhD in the study of lakes, Limnology. And that was, again, just the coolest thing, that I got to get a graduate degree. I got to do field work on the Great Lakes, where I fell in love with the Great Lakes, which I'd never seen before, being from the East Coast. And I got to work on a problem that was front and center of the 1970s and 80s, which was toxic chemicals getting into water from the atmosphere. And I studied PCBs, polychlorinated biphenyls, that were found in everything at the time. And they had been banned by 1976, but they were coming down into the Great Lakes in rain and getting into the fish. And so I was studying that process of how they got into fish and how they got into the bottom of Lake Michigan at the time, looking at the bottom mud of Lake Michigan. And again, I got to go out on ships, I got to work with wonderful people, and I really was amazed at how fun graduate school was. And then I got lucky, and I worked for a great postdoc advisor at Indiana, University of Indiana University. And then I came up here to Minnesota for a job interview, and I got hired, which was, again, I was just plain lucky. There was a job opening when I was looking for a job. I interviewed, I got the job, and I got to come to a Big Ten school that was close to the Great Lakes, and so I could continue this passion of working on how toxic chemicals behave in the Great Lakes. And so then I just, I got to spend all my summers out on field trips out on the Great Lakes. I got to really study the thing I cared about, which was this toxic chemical issue, but I got to do it outside, and I got to work on something that turned out to be a very hot topic. And so then I realized it parlayed into policy. So people began to ask me, I got interviews from the press, or I got asked to advocate in Washington for changes in the law. The work I did was relevant, which was, as a grad student studying what you love, you don't realize that it's important to other people necessarily. My passion was about what I cared about, and to see that it mattered to the nation on a national scale was a very eye-opening experience. So that's when I also first became interested in the whole connection of the work that I did, and writing another paper was interesting. Working on policy and how the work and the research I did, the fact that those papers were read by decision makers and policy makers and turned into policy was very rewarding. And so that really that's where I got the bug to do policy as well. And so my career has moved around such that I was able to actually then work on policy when the state asked me to help lead an effort to sort of design what the state water policy should be in order to achieve sustainable water use. This is after the Legacy Amendment passed in 2009, and we were able to create the Clean Water Fund and actually invest in Minnesota's waters in order to protect and preserve and enhance them. And so the legislature asked for this, and so I helped coordinate this huge effort to develop a statewide policy on sustainable water. And that was terrific. And again, it was the timing. I was kind of lucky. I was in the right place at the right time. But it really worked off my passion for science, water, policy. So I've been able to do that the past several years. I've continued working with the state on water policy issues. I work with the federal government a little bit with US EPA. And I get to live my dream every day. It's pretty cool.
So what's the mix of activities? I mean, are you still going out on boats and, or do you do lab stuff, or, how does it come together? It's a career.
Yeah, this mix has really changed a lot. So when I was early in my career here at the University of Minnesota, I was in the lab a lot, and I was training graduate students to be in the lab and do lab work, and then we would do lots of field work. And the research that I did was largely based on going out on research vessels and spending, a week or two gathering the data you needed to then, test a hypothesis or do an experiment. As my research progressed more into the policy realm, I had to give up the lab side. It takes a lot of money and attention and time and dedication to run a laboratory. So I moved away from the laboratory and focused more on results and translating that science into policy. And with that, I gave up the field work. So I haven't been out on a research vessel in a long time, except to demonstrate for students. So I taught a class on the Great Lakes for the honors program here at Minnesota. And as part of that class, we would take the students out on the university's research vessel up in Duluth, the Blue Heron. So my last few trips on a research vessel were one-day trips, just showing students what it's like to be on a research vessel. So I've had to give that part of it up, but I fulfill that need in my non-professional life. My husband and I are avid scuba divers, and we more and more we travel all over the world and see the amazing things that are on our coral reefs around the globe. So I kind of fill in the need to be on a boat by going out scuba diving.
From a chemical standpoint, what's interesting about water?
That's a great question. From a chemical standpoint, water is one of the most unique substances on the planet. It's a liquid that gets more buoyant when it freezes. That's why ice cubes, rise to the top in a glass. That's the only liquid that does that. It's only made up of two elements, hydrogen and oxygen, and yet it has the ability to dissolve all sorts of things. You can dissolve salt and sugar and minerals, and it is the universal solvent on the planet. That's how the oceans have minerals in them, is because rain falls on mountains and dissolves the minerals from the rocks, and it brings it down to the rivers and brings it out to the oceans. So water is the reason we can live on the planet, but the reason we can live with that water is that it's a universal solvent for giving us the nutrients and the minerals that fish and the ocean life need, but also that we need.
So, from a chemical standpoint, are there mysteries about water?
Oh, I think there are definitely mysteries about water. It's mysterious as to why does it behave as this universal substance, this universal solvent. We're doing this planetary research now, interplanetary research, NASA is looking at Pluto as we speak right now, and they're looking for signs of water. They look for signs of water on Mars when they send a mission to Mars, because then you can have life. But that's kind of a mystery into itself. How is it that water, not only is it necessary for life, but perhaps it's what helps create life? And so I think there are fundamental spiritual mysteries to do with water. There are chemical mysteries to do with water. How does it, we know chemically, we can describe why it works as a solvent. I can give you angles of bonds and all that kind of thing, and polarity and all of that. But still, what an incredibly unique substance. It's only made up of two things, and it has all these amazing properties.
So, back in your lab days, what kind of questions were you asking about water?
Probably the biggest question that I spent about 10 or 15 years addressing was when you have a chemical in water, and in natural water, so you're talking a lake or a river, how does it distribute itself between the chemicals that are in the water, the solids that are in the water, the particles that are in the water, and how much of it stays truly dissolved? And the reason we care about that is that if you drink the water, you as a person, your exposure is the dissolved part. It's what's truly dissolved in the water. If you're a fish, you might get exposed because you're eating those particles, which are actually algae or zooplankton or something good to eat. And so how much of the contaminant, the chemical, the bad chemical, is on particles versus dissolved in the water has everything to do with the ultimate toxicology of that chemical and what it's going to do to fish or to humans or to dogs or whoever is drinking that water. It also matters how much do you have to clean up the water. Do you just have to filter it, and that's where most of the chemical is, and so you don't have to worry about the dissolved part, etc. So understanding that is a key question to protecting public health, and that's where my lab was in the School of Public Health. So I wanted to understand those kinds of basic chemical distribution questions. Now that may seem like a pretty, like it took me 15 years really to answer that question, but the thing is it's dynamic. The chemical is changing where it is between particles and dissolved phase all the time. So it's not like you can just measure the water, filter it, measure the filtrate and the filter and say, well, now I have the answer. You really have to do a lot of studies, understanding the rate at which it is going to change from being dissolved to being on a particle, and the rate at which it will dissolve off a particle and be truly dissolved, and what are the factors that are going to affect that? Why is it going to change? What are the things that affect all that dynamics? In the laboratory, in a beaker, you can do that experiment and it's no big deal. In the real world, it's changing all the time. Temperature's changing all the time. The currents are changing all the time. You have different penetration of UV light on the surface of the lakes. There's all these natural things that are affecting that partitioning. And so we were trying to really get down to understanding all of the factors that affected that partitioning and what that partitioning was, so that the toxicologists could then make much better decisions about how to protect public health.
So what does it look like at the extreme ends? I mean, what's the perfect storm of this stuff gets in the water, we're in big trouble, and what's the best case?
Yeah, okay. There are a couple things there. I'll give you the best case first. That's a little simpler. So the best case would be it's all in the dissolve phase. There's none in the particles. Because if there's none on the particles, it can't go to the sediment. It just stays in the lake, and then it can break down by bacteria, by UV light. So the best case scenario is that these chemicals would not partition to any kind of solid. They would be purely dissolved, and they would break down by natural processes. They'd be gone in weeks, months, years. The worst case is unfortunately kind of what we actually found. So these chemicals strongly bind to particles. In fact, they don't just bind to any particle. These chemicals, like PCBs, bind to algae, to phytoplankton that are growing in the lake. And that complicates things. So these aren't static amounts of particles. These are particles that are algae that are coming and going with phosphorus and sunlight and temperature, and they're growing. They're plants, but they're alive, and they bind a whole bunch of these chemicals. It turns out they were like sponges for PCBs. So you could think, okay, great, go harvest the algae and you'd be done with it, right? But the problem is that the fish love those algae. Those little sponges taste really good. That's their main plant food. That's their vegetables. So the fish would eat these plants, and then larger fish would eat the smaller fish, and larger fish still would eat the medium fish, and so it gets passed up the food chain. These chemicals don't get broken down in the gut. They just keep accumulating. And that perfect storm is once they've been sorbed to the algae, they biomagnify up to those top fish by not just a millionfold, but like 10 to 100 million times. So the concentration in that big fish is 10 million times higher than it was back in the water in the partitioning phase. We eat those fish. We love those fish. These are the sport fish that people like to go out and catch. And so that's the problem, is that you get these incredibly high doses of chemical by eating those fish, that it all started back in the water partitioning to those phytoplankton. So even today, PCBs have been banned for, 25, 35, 40 years. And the fish in the Great Lakes still have advisories on them to say, you can catch these, you can even eat these, but don't eat them too often because they have toxic chemicals in them. Because the toxic chemicals continue to just recycle in the lake, and those fish have a high dose.
So if I'm getting you right, another piece of the magic of water is that once stuff gets dissolved in it, it tends to fall apart in various interesting ways.
It leads to different pathways, yeah. So some chemicals, when they're dissolved in water, it may allow them to be available to UV light to get broken down and made less toxic. In other cases, the water may protect them and get them to go to the algae. We don't really want to dissolve a PCB. We're going to put it on an algae. And then that leads to this other unintended magnification of the toxic chemical, leading up to fish contamination.
Now this is the story for PCBs. Is it going to be a comparable story for other contaminants, or does everything work differently?
There are groups of chemicals that behave similarly. And so I studied PCBs as it's a group of chemicals, by the way, we call PCBs. It has an S on the end. It's actually about 100 chemicals mixture. It can be used as a representative group of chemicals that includes all of those like nasty chlorinated pesticides that you hear about from the 1960s and 70s. It looks just like DDT. DDT looks just like PCBs in terms of its behavior. Chloridane, all those other things that have chloro in them. Those chemicals, about 15 really, really toxic pesticides from the 60s and 70s, those chemicals all behave like PCBs. when we banned PCBs, we also banned DDT, we banned all those other chlorinated chemicals or restricted them tremendously. We thought the problem would go away. But the thing is that it's chlorine that gives them that ability to last so long in the environment, and it makes them toxic. And so what the chemical industry did was said, okay, we won't use chlorine anymore, we'll use bromine. Same kind of family, it's on the same part of the periodic table from chemistry. And so they put bromine on these chemicals instead of chlorine. And the problem with that is it still makes them last really long, and it makes them pretty toxic. So we now are dealing with a whole other set of chemicals that are the brominated chemicals that behave a lot like those chlorinated chemicals, and they are still in use. So we're just now beginning to ban those chemicals. But we have quite a legacy of very persistent toxic chemicals.
Right. Well, so let me understand how this business with the law went. We said, we know this chemical does all sorts of nasty stuff, so we're going to get rid of it. Now, we're not putting any restrictions on what people could replace it with. We're not bringing in anyone who knows any chemistry to suggest a broader law than eliminating the specific thing. It's like, you may not shoot me with a gun, but a bazooka is fine. It's not exactly a gun.
You're partly right, but not completely.
Okay,
but I understand
okay.
why I gave that impression. Chemicals and the safety of chemicals is regulated within the United States by the US EPA under the Toxic Substances Control Act. And that law basically says, okay, we know there are toxic chemicals out there because we've seen what happened with DDT and we saw what happened with PCBs early on. So we know there are toxic chemicals. So we want to know how many chemicals the industry is making and for what purpose. And any information you have on those chemicals, any toxicology, we want you to file that information with the federal government. But all the chemicals you're currently making, we're just going to grandfather it. We're not going to say whether you should or shouldn't make those because we didn't have this law in place until 1976. And a lot of these chemicals were made in the, as I mentioned, the 50s, 60s, and 70s. When they banned PCBs, well, and the other part of our law is a chemical is legal until it is proven that it's guilty. In other words, it's assumed innocent until proven guilty. It's assumed that it's non-toxic and not harmful to the environment until there is evidence to show that actually it is harming the environment, and then we go about doing something to regulate it. It's a pretty onerous process. And it took a long time for even those chlorinated chemicals to be thoroughly banned as a result of coming up with all the evidence to show that they have toxic effects. The brominated chemicals were brought onto the market, but again, they simply registered these chemicals, and I'll give them a little break. They thought bromine chemicals were going to be a lot less toxic. They just didn't have any evidence to show that they were going to be toxic. And the fluorinated chemicals, the same thing. Fluorine, bromine, chlorine. They put some new chemicals on the market and thought they were not going to be toxic. And consequently began to manufacture them in huge amounts. And it turns out that all of those chemicals have some toxicity. And they behave similarly, meaning that they're very persistent. They get into the food chain. Humans are exposed mostly by eating food. So that's the problem with them. Mostly fish. But even polar bears in the Arctic have these chemicals in them because they're eating fish. They're top predators and they're eating fish that have gotten these chemicals from atmospheric transport and then come down in the snow and they get into the fish, and that's so they have the same problems all around the world. So our chemical safety laws really are, they're a little outmoded. They take years and years to react. They assume that a chemical is non-toxic until it is shown to be toxic. And there is some effort to be changing that. There's actually two bills, and there's a bill in the Senate right now that is being considered to change that law to make it a little tighter so something like this wouldn't happen again. The European Union, by the way, considers chemical management completely differently. They assume a chemical is guilty and is toxic And it's up to the company that manufactures it to show that that product is safe. So they have a very different approach to chemicals in the European Union.
You did this 15 years of lab work to see what was happening with PCBs. Would it have been possible to do a comparable 15 years of lab work to see what was happening with these bromine things?
Yes, in fact, ultimately, we didn't do the same experiments on the brominated compounds, but we did sample the Great Lakes for them and found them in the same abundance and having the same bioaccumulation problem. So those 15 years were spent not just in the lab, but also then verifying what we could model in the lab. Then we'd go to the field, we'd collect Great Lakes water samples, fish samples, algae samples, and then we would see if our hypothesis was being borne out for real in the real world. And when we tested the same thing with the real world samples for brominated compounds, they were the same. We didn't have to go back and do the lab experiments. We kind of had the real world evidence that they were accumulating in fish at the same levels.
So if someone comes up with a new chemical they want to introduce into the environment in massive quantities, how much can one know from the kinds of lab work you were doing about what it's likely to do?
You can make some pretty educated guesses, and I won't say it's because of my lab work per se, but one of the things that our work did, and many others at the time, we could show that the behavior in the laboratory and in the field, in the Great Lakes, you could predict it from certain chemical properties. So if you knew certain aspects about the chemical, everything from its vapor pressure and its molecular weight and its chemical structure, its solubility, we could, that's back to the water thing, water solubility, we could predict reasonably well what a chemical, how it would behave in the real world. So if you know those properties, then you can kind of say, this chemical is going to be a problem in the real world. It's going to accumulate in algae, it's going to get into the food web. Now if it's not toxic, we don't care. But usually these chemicals, the toxicity goes with those properties. So you can predict you can basically flag chemicals based on their chemical properties alone and say, these chemicals are probably going to be a problem and we need to do studies on them, like toxicity studies and measurements. And these chemicals, they just don't have any properties that make them particularly dangerous, and so these are okay. So we were verifying that you could take these kinds of chemical properties, predict what you saw in the lab, and then predict what you actually saw in the environment.
And if I understood what you were saying a minute ago right, in the European Union, if you flag something that somebody proposes as being dangerous or likely dangerous based on these properties, they're going to have to do quite a lot of convincing before it gets into water in massive quantities.
That's the theory. You know, they started this process, it's been in full force maybe only a few years. They started it more than a decade ago, but you know, to get all these countries and chemical manufacturers up to speed, there was a certain amount of time lag to do that. So that's true for chemicals that you were to bring to this today to the EU and say, I want to make this chemical. They could make that kind of a decision. But the older chemicals, they the companies that made them had to kind of circle back and say, you're right, these are kind of toxic, we're not going to make them anymore. Or the EU would say, we're not going to grandfather in these chemicals, we're actually going to ban these chemicals. So the EU, for instance, has lots of restrictions, if not an outright ban on atrazine. That's a pesticide, or excuse me, an herbicide. And the United States restricts its use to certified applicators, but it's not illegal, it's not banned. And that's because they really viewed the risk of having it in the environment differently. They have a different bar of what's safe and what isn't safe, and a different process for getting there. So it's beginning to work in the EU to protect public health, but it's an expensive, there are trade-offs in this. It's expensive, and the chemical industry, however, then is, they get pushed to do more innovative things, to come up with better chemicals and safer chemicals. So there's a good thing about this. It's not all negative about banning chemicals and, it's not, the bad chemical industry. It's really about, okay, we can all agree that these chemicals really shouldn't be in the environment. Let's find, you guys are the PhD chemists, go come up with a better polymer or go come up with a different chemical that's going to still make our lives function nice and easy the way we enjoy chemistry.
So, if I'm getting the European situation straight, you've got two things going on. One, if I think up some nifty new chemical, somebody's going to look at it and see if it has properties that make it extremely suspicious as a major component of, let's say, the environment. And the other thing is they aren't in love with grandfathering in everything else in quite the way that American regulators have been. Have I got that right?
Yes, then there's a third piece that's quite different, which I think makes a difference. And I think we're moving more toward the European model here. But in the European case, if you're a company and you're going to create this new chemical, you are going to do all the work necessary to convince the EU that this chemical is safe. You're going to do toxicity tests, you're going to get all those chemical properties, and then you're going to put together a dossier that says, here's my chemical, I think it is safe to use. The industry produces that evidence. And the EU is simply, there's not enough money in the world or enough people in the government to do those tests themselves or to make an independent decision. So they have to trust the industry to self-report and have that be accurate. And there's, the EU they've made that choice to do that, and it's not a bad thing. It's actually using the industry to help support the industry. The industry can then do those tests in-house, they can do the toxicology in-house, and there's no reason not to trust those data. And then the government isn't doing it for every chemical company. If the chemical companies are doing it, and the manufacturers. In the United States, we didn't say that back in 1976. We said, you tell us the basic information, and if there's a problem, I guess we're going to have to figure out how to regulate it. And that put the onus on the government to show the chemical was bad. The government doesn't have enough people or money to do this for all the chemicals that are out there that are of concern. So this, the change in the law includes moving some of that responsibility back to the industry, back to the private sector, because the public sector can't handle it. There's too much to do. So that's a change also, is that in this country we've not relied on the private sector to carry part of that weight.
Yeah. Is there a worry about the falsification of results?
I'm sure that there is, and I'm sure that back when the EU put this plan together, that was probably one of the main discussion points. But I do not know of any case where there's been the falsification or the misrepresentation of data, because once the data, the dossier, is put forward to the EU, there are people that review it. And this isn't being done in a vacuum. These chemicals, lots of them have been studied by lots of scientists, such as myself, around the world. And so there's published literature on these things. And so if they would be, I don't think they would take the chance. A major company isn't going to take a chance to falsify information when, in fact, the world is too flat today. We can get other information from other places. And it is reviewed by very competent scientists. So it's not that they just say, the chemical's fine, trust me. It's actually reviewed and goes through a review process.
So how much influence does the European Union have on chemical policy in the United States? I mean, a very simple thing is they can buy or not buy fish. I mean, how much, is there pressure? What are the means of pressure by which a European Union standard that is stricter than the U.S. standard
so they
reflects
don't allow
back on us?
Yeah, they don't allow the imports of these chemicals or the products that they're in. So it's not so indirectly down at the fish level, it's way up at the manufacturing level. So take our own company 3M. They make a product that is not allowed in the EU, but it is allowed in the US. So are they going to change their manufacturing and have one product that they can sell in both markets, or are they going to make two products, which is a lot more expensive and complicated? Because then you've got two markets and two sets of paperwork and all that. So if you've already made the product that's going to work in the EU, why not make that product and market in the US? So the pressure is one of practicality to the big companies. 3M is a global company. If they're going to be part of the European market, they have to conform to the EU system. And so they don't really want two systems. I'm sure if you ask the CEO of 3M if that's a true statement or not, I don't know the answer. I've never heard 3M actually say, we would like to not have two systems. But it just makes sense, and it makes sense that they would not push back against this new law in the United States. And that's what you're getting, is that the law that's being debated in the Senate is not getting pushed back from the chemical industry.
So in this instance, free trade and global markets push standards towards the more restrictive end.
It's one of the few examples of that, I think, where we usually think of free trade as, it's going to hurt other countries because they don't have the same environmental standards. And that's a lot of the debate around trade, although that's not my specialty. But yes, this is a case where the process and the management and the rules in the EU are stricter than in the United States. And so it is having an impact on other manufacturing markets. The United States, Japan, China, they have to conform to EU standards to be part of the EU market. So I think that's an interesting case where the United States is being pushed a little by rules that are stricter than their own.
So how does it work within the United States? I mean, do states have any independent judgment on the chemicals in their boundaries?
Yes, they do, and Minnesota is no exception. Minnesota's been somewhat of a leader in taking the bull by the horns, and if the federal government isn't going to regulate certain chemicals, they will regulate certain chemicals. The state of Maine has a couple of state laws in place. Massachusetts has some state laws in place. California has been a big leader in this with their propositions and banning certain chemicals based on their much higher bar of what's safe or not. So yes, the states have the rights to do that. Counties can even do it. You can have a county pass a law through their government system that would restrict the use of a certain pesticide or something. So you can have sort of chemical-free zones for certain chemicals. Now, that's not a very effective thing to do. You don't really have a lot of leverage, and again, the companies don't want to see this happen because you get this patchwork of laws across different states, even at a sub-state kind of level. So everyone that I have, most people that I talk to, both the environmental side and the chemical side, they would prefer a single set of rules, and they agree that the 1976 law is pretty out of date. It's never been modified by Congress. It's one of the few major environmental laws that's never been amended, and this would be an update to that law. It's not perfect nobody's perfectly happy. The chemical industry would like probably no law, and the environmental organizations, the more extreme ones, would like to see chemicals be, tested and banned if they have any toxicity at all. I mean, there's an extreme on either side there. The proposed new law, it's different from what passed from the House, so there's still we don't know what the final law will look like. So the House has already passed the amended law, and now it's in the Senate. And how that plays out will depend on lots of negotiating. Were there compromises made? Sure. But it does try to provide for one set of rules that we can all live with, that do protect public health, take a more um, guilty until proven innocent, a more precautionary approach to managing chemicals, as well as holding the industry a little bit more accountable for these chemicals. So there's give and take on both sides of that.
Do you know how that interacts with legal liability?
No.
Okay. The question, just to say it, is if we have a standard, a generally accepted universal standard, and it turns out that it's killing quite a lot of people, that activities under that standard are killing quite a lot of people, and 3M was the company that made all of the chemicals that were killing those people, have we got then, is it a get out of jail free card, or at least a get out of massive damages free card?
I don't believe so. But I don't know the specifics of how liability works in the new version of this. And so, yeah, I don't know how that's going to play out.
Because the one interest that industry would seem to have is to have a standard such that the costs then fall on the public,
yeah,
and not on them if they goof.
Yeah, and yeah, I'll just say I don't know enough about the specifics, but they don't get a get out of jail free card unless they're following the law. And if they're following the current law, they should be okay. But if I'll just say that under the Superfund law, those companies that did pollute, even though it was legal at the time, so pre-1970 whatever, those companies are still currently being held liable for cleanup, even though when they discharged those toxic chemicals, they were legal to do so. We had no national, we didn't have the EPA, we didn't have national rules. And so there you have a liability which basically says, okay, we know you didn't mean to do this, or maybe you did, but we didn't know it was toxic, or it doesn't matter what the argument is about the chemical. It's toxic, you polluted this site, you polluted the river next to it, and you are liable for those damages. And that's very clear in the Superfund law. How it extends in this TSCA law for public health, I don't know.
So what's your work like in producing public policy on water?
So having been part of this effort, been sort of the ringleader of putting together the Minnesota Water Sustainability Framework, which is this 25-year plan for how to get the state on the right footing for sustainable water management. That plan is, it's been in play for about 5 years. The legislature didn't pass it, they didn't embrace it. It's really been implemented very piecemeal, which is fine. I wasn't out to have the whole plan adopted as a political process. But it did educate the state tremendously on where the problems are. Before this plan was put out there, nobody in the state was worried about our overuse of water. Nobody was concerned that we were using too much groundwater. And now you hear about that all the time. You hear about the White Bear Lake situation. You hear about the Metro water plan and how the fact is we're using too much groundwater. We should be using more surface water because it's much more renewable than the groundwater. So a lot of these issues were brought up for conversation. And we offered solutions, but any solution, as long as it's a good one, is fine. So I continue to make sure that these issues, as an educator, as a professor at the university, my role has been to educate as much as possible and advocate for what I think are the necessary steps to take. Not the specific answer, I have my opinions, but as an educator, it's to say, here we have a major problem with runoff from row crop agriculture. It has polluted our groundwater, it pollutes our surface water, and it contributes to the Gulf of Mexico dead zone. We can't just pretend that just because we like agriculture and we're an agricultural state that we can't just ignore that. We also have to deal with protecting water quality. It's our citizens' public health, it's our environment. We need to do that as well. So trying to educate about both what the problem is and what could be done about it, and try to start those dialogues. There's not one answer to how to fix that problem. There's many answers, but it requires political will and education. It requires people to really understand what impact adding fertilizer to a farm field, what the impact of that is.
If I'm understanding your situation right, you're in the position of having some issues within the policy debate be chemical issues, and some be maybe physics issues of a different sort altogether. I mean,
Yep.
How fast are we depleting our groundwater, and how fast can it be renewed, and matters like that. So how do you find this business of working partly in an area where you may know more than anybody, and partly in areas where somebody else's expertise is relevant?
So the Minnesota Water Sustainability Framework used between 200 and 250 people to put it together. And so the short answer is I go to other experts that I know are the experts, that I trust their reputation, and they have an established, honest reputation and produce excellent science. So for the chemical issues, I also still go to other people. I'm not a toxicologist by training, so I also go to the toxicologists, or I go to the public health folks that do risk assessment. So my role of educating is to first educate myself, make sure that I know what I'm talking about, push for education to our citizens and to our decision makers. And when I don't know something, it's bring in other people to make sure that we are presenting the science to not just educate, but the science on if you do this, this might happen, if you do this, this might happen, so that the science is being used to help come up with the right solutions. But no, I would never do this alone, and I don't do it alone. I rely on lots of other colleagues,
What's your sense about how much we know?
About?
What I mean is, when we put together a water sustainability plan for Minnesota, how much of our understanding of what happens with water is firm, and how much of it is still pretty shaky?
I don't know how to put a percentage on that because it varies by issue. We know we're using lots of groundwater. Can I tell you what percentage of our total water supply is being depleted? We don't know that because we don't know how much groundwater we have, to the nearest, 10,000 gallons. We don't know that. We just know we're using it faster than it's going back. It's like a bank account. We might not know the balance in the account, but we know we're spending more than we're depositing. That can't go well. So that's what we're doing with our water. So we're missing but how much is there? And we're working on that. The nice thing is that when this report came out 5 years ago, the legislature did respond with investing in more research being done by the DNR and by the Geological Survey, the Minnesota Geological Survey, to understand those things better. So there's a lot more. Our knowledge gaps are being filled much more quickly as a result of that report. The other thing that we don't know gets back to this chemical issue. Some of the issues are political. They need a political solution. Some of the issues are we actually don't exactly know how to proceed because we don't have enough information. So I talked about these toxic, persistent chemicals, but we also have hundreds of other chemicals that we refer to as chemicals of emerging concern. We know their chemical properties, but we don't know enough about how to predict not only their behavior, but we don't know how to predict their toxicity. We just know that many of them can interact in the environment, specifically, we have lots of data on fish, to change their reproductive success, to change their behavior, to change their growth, their development. And now there are studies that we can link that to human growth, behavior, development, reproduction, but we don't know it chemical by chemical. And to get all of that toxicology data is almost an impossibility. It might take 100 years to do all the tests the way our laws require them. So these chemicals aren't regulated. We don't have enough data to regulate. And so that's a huge knowledge gap. And so we know they're a problem. We know we have hundreds of these chemicals in our environment, not just dozens, but hundreds. We know that some of them cause problems with fish and with humans and with birds. We don't know how to regulate them because we don't have enough specific information to regulate them. And so the state has kind of got its hands tied. The federal government has the resources to do that. And so the state, you know, we're sort of sitting here knowing something, but we can't do much about it because we don't have enough information. The federal government is moving to get that information, but it's still years away. So that's an example of a big data gap, knowledge gap, and it means that we can't even design good policy because we don't have enough information.
So do the epidemiologists get into the act here too? I mean, the information about, I mean, one way to go is to say, okay, back 50 years ago, we didn't have these chemicals. What's happening to cancer rates? What's happening to miscarriages? What's happening? Is that coming into the picture too?
Absolutely. When I said we know that it's affecting humans, some of these chemicals are affecting humans, it's through epidemiology studies that get paired with or matched with the data that we have from animal studies. So you can take a chemical or a group of chemicals and expose them to mice and show that at a certain exposure the mice stop reproducing. Okay, that would be an example. Shuts down their reproductive system. You can't go and give humans those chemicals, you know, in a dose-response kind of controlled experiment, but you can then see that if this cause effect you've demonstrated with mice, whether you see the same impact in humans. So you can go and look at levels of that chemical in the bloodstream, say, and look for data epidemiologically in populations for reproductive problems or something like that. And then you can say, okay, the mice showed us the cause and effect. We don't have cause and effect with the human data, but we see the same impact relative to their concentrations in their blood. So you can begin to draw some strong conclusions based on the body of evidence, the whole, you know, collection of evidence. And what we know is that from those kinds of studies, with animal studies and then looking at population studies, and a lot of this is being done at the federal level by the National Institutes of Environmental Health Sciences, we know that these chemicals are linked to reproductive problems, linked to things like diabetes, obesity occurrence, heart disease, and certain behavioral issues. There's no firm evidence, but there's some concern that it's related to things like ADHD. So when I say behavior, I mean like children's behavior. We know that it affects children's development from exposure in the womb, again, from doing it with mice and then actually seeing effects in populations. So there's a lot of concern about these chemicals, but we don't have enough information to say this chemical should be regulated at this dose because it would require so much to even regulate one of those chemicals, much less many. And they don't behave similarly. Like when I said I could use PCBs to predict DDT and dozens of other chemicals like it, you can't do that with these chemicals. They don't behave in a pattern that allows us to make those leaps of faith yet. So I'm hoping someone is doing the same kind of research I did to try to make those connections so that we can predict the chemical behavior and not have to do a gazillion measurements on each of them.
Well, I take it if you run the timeline back 30 years or so, a lot of these chemicals weren't there yet, right? I mean, a lot of the things you're talking about.
They all popped up post-1945.
Pretty recent, you know, relatively recent.
Yes.
Are they coming in massively? I mean, how fast are these hundreds of chemicals that might be culprits sort of being added to our environment?
At an accelerated rate, certainly since the 1950s. And so a lot of these chemicals are synthetic chemicals, and we learned how to synthesize organic chemicals during World War II. And that led to synthetic rubbers and synthetic plastics, all made from petroleum, interestingly enough, and lots of polymers. And so if you just look at plastics, all just by itself, there's so many kinds of plastics. There's saran wrap, there's plastics that cover things, there's hard plastic like a cup, there's plastics used in baby teethers, there's plastics used to seal cans. There's so many different kinds of plastics, and it's the same concept of starting with a base polymer and then adding things to it to make it stretchy or pliable or opaque or clear or some other property. And those additives, as well as the initial plastic polymer, it turns out they are all contributing to this soup of potential effects in the environment, because this isn't coming out of a pipe where we could say, okay, we should stop letting this company discharge this chemical. These are in our everyday product. You look around your own home, you will find, I don't know, a dozen different kinds of plastics, and they all have chemicals in them that make them useful as plastics, but they also potentially can be causing this harm. So you throw away your plastic covering, or you even recycle it, or whatever you do, but the plastics get moved around in the environment. They go into a landfill, they get chewed up in a recycling something. Those chemicals get out into the environment. And so we see these chemicals in the environment, but they're coming from all over the place. They're not coming from a company that we can say, okay, we're not going to let you use that chemical anymore, or make that chemical, or discharge that chemical. So getting to the root of this is orders of magnitude more difficult, I think, than the problem we faced in the 1960s with PCBs. I think this is a much larger, bigger, more insidious problem. PCBs were related to cancer, and they were regulated for cancer, and then for reproductive problems. They definitely were causing reproductive problems. These chemicals, we're talking about being related to, but not causing, diabetes. So you have to understand the diabetes, you have to understand all the other triggers, you have to understand genetics. It's complicated, very complicated.
So we've got Murder on the Orient Express with, 1,000 suspects instead of 12.
Yeah.
And all of these chemicals are, it isn't like they're being modestly promoted in anticipation of possible problems. So what's keeping you from despair on this one?
I get asked that a lot, actually, because I do study these kind of recalcitrant problems without real clear solutions. I think, the honest answer is that I compartmentalize. I am able to deal with, nasty problems because that's a nasty problem there, and then I can think about something else, and that it's compartmentalized. So I can think about the beautiful fish on the reef. I can think about the beautiful place that we live on a lake in Minnesota. I can think about the relationships in my life. I can think about, my brand new grandson, and I cannot have those chemicals interfere with those too much. Sometimes I worry about that grandson, but there's not much I can do, so I compartmentalize it. That's the honest answer of how I deal with those things. But I do think someone has to continually think about them for us to find these answers. For us to, if it's not 10 years from now, 20 years from now, I don't think these are easy answers. I think they are decadal kinds of answers to get at protecting our environment, protecting our public health more effectively. But someone has to keep doing it.
How do you understand Minnesota as an entity with respect to this whole matter? Are there special hopes? Are there special problems? What chance does Minnesota have of addressing this problem that is everywhere?
Yes.
In some way worse or better than other places? I'm sure better than some places. We've got a whole lot of the state with less than 1 person per square mile, right? I mean, we've got a whole lot of place where nobody's pumping much of anything into the environment because nobody's there to do the pumping. People haven't found a use for it yet.
Yeah, but water and air have a way of moving across boundaries.
Yeah.
But I'm not from Minnesota. I was born and raised in New Jersey, and I moved around the country. But I've spent the last 30 years, so half my life I've spent here in Minnesota. And I have such regard for this state. I don't think anyone will ever call me a native Minnesotan. I'd yet be born here to earn that. But I have such regard for Minnesota, and it's because the people and certainly over those 30 years, but historically before then, the people of Minnesota have a certain ethic and morality and set of principles that they want a good life, they want a good standard of living, not the best, they're not greedy, they're just above average, as Garrison Keillor would say. They want a good life. They want a clean environment. They are used to having a beautiful state, and they value that, no matter who you talk to. A farmer values that beautiful field of his and the soil that he gets to use, and a person who runs a lodge up in Ely, obviously loves the land and water and air. They value the state at a level that I find above other states. And I travel a lot, and I see it and talk to lots of other people. And the value system that is here in Minnesota that's been generation after generation, people care about the environment, they care about health. They want to be healthy, they are healthy. We have a pretty healthy state. They want to protect what they have, and they care about their grandchildren. They care about that ethic of making sure that you leave the world a better place for your next generation. And I see this acted out in all sorts of ways. You don't have the same level of antipathy or lack of education. People understand their environment. Might be a very simple way of understanding simply its beauty, but they are aware of their environment. There are very few people in Minnesota that can't talk to you about, how do you feel about your environment? And they'll talk to you, whether it's the creek in their backyard or the fireflies they see in the summer. They can tell you something about their environment. And a lot of people in the other part of the world, in this country, couldn't. They don't have the same appreciation. And this has just been instilled generation after generation. Now, Minnesota also has a very, typically, regardless of your politics, they tend to be pretty progressive on the environmental side. And I believe it's to protect, it's a result of this ethic that is in people. It doesn't matter if you're at the Iron Range or if you're from the southeast Minnesota farming communities or the Twin Cities. I think that ethic is shared by just about everybody to some degree. As a result, we have strong environmental laws. As a result, we have good debates about our environment and public health. We have good leadership at the state level, and we have regardless of who's been in power. I mean, it's not a party thing. It's really, the state has always done things that are pretty much to protect the environment. I mean, there's steps forward and back. You can argue over the nuances, but if you look over the whole history of Minnesota and protecting its environment, it has done so consistently over time. And we also have strong actions. We are the first state to have a complete water plan of the kind that we put together. And 250 of the best water experts in the state put together a plan. It's unprecedented anywhere in the country. And we have people that read that and look at how they can make a difference. We have strong wetland protection laws because we value our wetlands. We have a strong groundwater law, which it gets stronger with each time we learn something that we want to protect the groundwater. The Governor's Buffer Initiative, not to get into the politics here, but that initiative is one of the first in the country to have the boundaries on it that basically says our water is public, it belongs to everybody. We're going to do this minimal thing to protect public water. That's That's a Minnesota ethic speaking. That's the Minnesotans speaking. Other states don't necessarily do that.
So, will it be like the European standards, the EU standards? Will we bring the country up to our level, or will we be outcompeted by cheap asparagus from New Jersey?
Now, don't despair New Jersey. I'm still a fan of New Jersey. I think that over time we have been leaders and we will continue to be leaders bringing up the country on these kinds of environmental issues. The buffer rule that just passed, a lot of other states are looking at that going, wonder if we have the, if we have the courage to do that, The state of California and is having this unbelievable drought. They're being pressured in ways that we can't even begin to fathom. We just can't imagine not having the water that we have. And yet we have a groundwater law. California just passed their first groundwater law a few months ago. To us it just makes sense to protect these things. We are making some progress with trying to get our water quality goals in line with our agricultural production goals. It's not perfect. We have a long way to go, but this state is moving towards having not just a dialogue about it, but actually doing things, actually saying, okay, we need to do these things and then kind of see how it goes, and if these things work, then we know we're on the right path. So it's a combination of working with the farming community, a little bit of regulatory boundaries, but trying to really get the farmers to understand that they can have both high production, good incomes, and they can also protect the environment. And we're a state that is doing that in a way that is as collaborative as possible and not top down, crack the whip. And that's a good model for other states. I don't think anyone wants to see top down, everyone has to have a permit kind of approach to protecting water from agricultural runoff. But there are ways to do it to make progress that the state is exploring, and I think other states are very much watching to see what happens. And we don't do a lot with lawsuits. That's the other thing about Minnesota. We're less litigious, is that the right word, than a lot of other states. A lot of other states, this company's polluting, or this is out of compliance, in come the lawsuits. That eats up a lot of money and time. Sometimes it's appropriate. Absolutely. There have been movements forward as a result of lawsuits. But it's not the first reaction in Minnesota. In Minnesota, it's, you might get sued if you don't do this. And then the state says, right, okay. And so that there's a lot more consideration of, let's avoid the lawsuit, let's try to comply with the law, whether it's the government itself being out of compliance with the law they're supposed to be enforcing. Sometimes that's the lawsuit, or sometimes it's a polluter. But Minnesota does a nice dance in terms of, they could have lots of lawsuits. But we're one of the few states that has not had lots of lawsuits, say, over the Clean Water Act. There are groups that threaten to sue, but they hold off because they'd rather work out a solution, they'd rather do it diplomatically.
Thank you.